All right, welcome back. And this is the last portion of the exam that we're going to go through. And you'll note that you don't need to give any explanations here, but I will so that you know why it is that certain answers are correct. And so you can use this to study for the final exam. Because not all of this material will show up there, but a portion of it will. So this is a good bit of study material for you. All right, so number 4, a ferromagnetic material has which of the following properties? Mark all that apply. As it turns out, almost all of these are correct for this, all right? So A, it has domains in which all the atomic magnets are aligned. I put magnets in quotes because you don't think normally of atoms being magnets, but remember they all have a little north and south pole. They're little dipoles right down to the atomic level, and domains are one of the distinguishing characteristics of all ferromagnetic materials. So A is one of our correct answers. B, it can retain its magnetic poles after a magnetic field is applied to it. Yeah, all other kinds of materials, and there are other kinds of magnetic materials like paramagnetic and diamagnetic, and we mentioned a few of them, none of those retain their magnetic poles after you remove a magnetic field from it. So you can magnetize, quote unquote, a ferromagnetic material, and so we also circle B. It has a stronger magnetic field than non-ferromagnetic materials. This is also true, okay? The reason why we use them in electromagnets and things like that rather than anything else is that they magnify the field produced by the current carrying wires by creating magnetic field that is very strong when you align all of the domains in that ferromagnetic chunk of stuff. So C is applicable. Now D is a little bit of a curveball, okay? So it is made of iron or an iron-containing compound. Now some ferromagnetic materials are iron or iron-containing. However, there's lots of things that are iron-containing, well, some things that are iron-containing that aren't ferromagnetic materials, stainless steels, for instance, and a fair number of ferromagnetic materials do not have iron in them. Neodymium magnets, I think another one, cobalt, we mentioned in class. So there's a few other examples that we mentioned in class and that were in your reading. And so this one, though sometimes true, is not a general descriptor for ferromagnetic materials. So I was looking for A, B, and C for this question. Now, number 5, consider a real battery. So it has some internal resistance connected to a circuit. What happens to the voltage difference across the battery terminals as the resistance of the circuit is decreased? Okay, so we know from Ohm's law that if we decrease R, okay, and we're applying X number of volts from the little ideal battery inside of our real battery, well, then current is going to rise. And if current rises, then the little internal resistor that is in series with the battery, because I should put an external resistor here, so this little internal resistor, that's going to experience more current. And so it's going to drop more volts, again due to Ohm's law. And so the terminal voltage of the battery would be smaller than it otherwise would be. So it decreases. Okay. A simple circuit is built. Number 6, you got this 9-volt battery. You put another identical battery in parallel with the first. Okay, so remember that in parallel doesn't do anything to change the amount of voltage being applied to the circuit. So the voltage applied to the circuit is still 9 volts because you've got a situation like this. There's our little light bulb, okay? So 9 volts across each branch. And that means that we can't change the total current because we haven't changed the voltage applied to the circuit, and it's the same light bulb, so that is out. Voltage difference applied to the circuit doubles. Nope, that would be as if they were in series. The light bulb will remain lit for a longer period of time. Bingo. Right now, each one of these batteries is only responsible for pushing half the total current. So each one will last twice as long than if there wasn't something in parallel here. And so that's what we're looking for. If you consider the other ones, it won't get brighter, okay? Same voltage, same current, and the total current in the circuit going down, no, that's not going to happen, okay, for reasons that we've already discussed. So, X. All right, one more on this page. An electromagnetic relay is a device that you could see elements of truth there, but no, not amplifies, not unless you have a whole bunch of other stuff going on, okay, outside of just the relay. Let's look for a more basic definition. Uses an electromagnet to open or close a circuit. Good, that's it. That's the kind of thing that we studied, and that's the basic function of what a relay is doing, though the attached circuits can do all sorts of other good stuff. Produces electricity from magnetic fields. No, that's a generator. Produces mechanical motion using an electric field. That is, well, that's nothing that we've studied. Guess it's used in a particle accelerator, but nothing else that we've looked at. All right, on to the next page. Number 8. There we are. When a magnet is subjected to a constant magnetic field, which of the following behaviors is observed? So think about the magnet as like maybe a compass needle. And think about the constant magnetic field as like Earth's magnetic field, right? Which is more or less constant in magnitude, though it does vary a little bit around the surface of the Earth. Okay, so A, magnet fields a torque until it's aligned perpendicular to the applied field. We're good there until the word perpendicular. B, the magnet feels a torque until it is aligned parallel to the applied magnetic field. That's the one. And this is right from the very beginning of our lectures on magnetic fields. So go back and check out that kind of stuff in those notes if you're wondering about this. The magnet is unaffected. That seems unlikely given that it has a magnetic field being applied to it. It'll feel some sort of force or torque. Constant torque towards the South Pole, well, that would require very specific circumstances. And E is just kind of something to hopefully amuse you as you took the exam. All right. Now, 9. Oop, went a little bit too far there. If a wire is carrying current flowing to the left, and the Lorentz force the wire feels is out of the page toward you, so point to the arrows, there's the F, okay, the force. In which direction must the magnetic field be? So let's see if I can get my hand in here. So FIB, so F towards us, and direction to the left for the current. And so my middle finger is pointing down the page in that orientation. And so, okay, right-hand rule for Lorentz forces. What is a clear advantage of an electromagnet over a permanent magnet? Simpler to construct? Not really. A lot of coiling of wire and whatnot, okay? Lighter? No, not for most electromagnets. They have an iron core, which is just as heavy as any permanent magnet material. It uses electrons. Sure, but why is that an advantage? Its magnetic field is easily controlled. That's the one, right? The whole thing of electromagnets is that you remove the current and the magnetic field basically goes completely away. And with a permanent magnet, you're kind of stuck with whatever magnetic field it produces unless you demagnetize it somehow. And that's, well, that's sort of going against the permanent part of its name. So, number 11. Brushless DC motor. So our 1 point on brushless DC motors on this exam does which of the following to avoid having a brush connection to its rotor, and mark all that apply. Okay, it has a permanent magnet on its rotor. Yes, it does. It has to have that to avoid having brushes. Its armature is moved to the stator. Well, that wouldn't work for a motor. We've already covered that earlier in the exam review. You have to have something moving to get mechanical power out of there, so that one's not going to cut it. Electronics and sensors are used to turn off and on the electromagnets on the stator. Yeah, so you need this sort of essentially rotating magnetic field that drags the permanent magnet on the rotor around in circles, right? That's how you get torque. So that thing is true. And D requires a small mechanical input to get started. I mean, ideally you wouldn't have to give a motor a push. I suppose in some circumstances you might, but it's not specific to the brushless DC motor. So that one's out. A and C. All right, we're on to the last page. Number 12. This one's a little wordy, but it's a good question. Makes you put on your thinking caps. So if you have an AC generator, so an alternator from a car, say, it has brushes connected to slip rings, and then they connect that to a DC power source, and that's how you power the electromagnet that's on the rotor. And the armature is on the stator, so that you can put a rectifier on its output really easily. You just hook it directly up. No further brushes or commutators or anything like that needed. In brushless alternators, the brushes are avoided by some cleverness. Which of the following is done in brushless alternators to eliminate the need for brushes? Pick the answer that 1 would work and 2 is most practical. Okay, so A battery is attached to the rotor, so it rotates right along with the electromagnet on the rotor and can be wired directly to the electromagnet. Okay, well that would be one way of getting DC power to the electromagnet on the rotor, but this would require somehow getting the battery attached to the rotor. And then if you think about it, eventually that battery is not going to be able to push current anymore, right? It's going to run out of charge. And so somehow you're going to need to get power to the battery to recharge it. So either you have to have a brushed connection again, or you have to be able to like remove it and charge it up and then put it back. And that doesn't seem very practical to me, though this would work. The armature is swapped to the rotor so the electromagnet can be on the stator and be powered directly. Okay, well if you did that, and you can do that, you can have the armature of a generator on the rotor, okay, you still need a connection, except in this case you'd either need a slip ring to get the AC power off, or you could use a commutator to connect to the brushes and get DC power directly from there, but you wouldn't be able to avoid using brushes. Both of those, slip rings and commutators, use brushes, so that one is definitely out. A commutator is used to allow the armature on the stator to power the electromagnet. Okay, there's all kinds of things wrong with this, but the primary thing is you see commutator, you know that commutators are connected to brushes to transmit power back and forth, so you know that this can't be the case because we're looking to eliminate brushes. Okay, D is the one that's most practical and would work, and this is how it's actually done. So let's parse it. Second generator is used with its field on the stator and its armature on the same rotor as the first generator. So what it looks like is, say you have like, a little block diagram here. You have your rotor going down the middle, and this is the electromagnet we need to power. And that the coils here and here on the stator would just carry the power out. Okay, so that's the first generator that we're talking about. Okay, so the second generator, well, it has its armature. So the coils where we're inducing the voltage on the rotor instead. And so we can just take the wires from the end of those coils, run them right down here. We'd need to put them through a little rectifier or something like that and hook them up to the electromagnet so we get DC power to the electromagnet. And then we can have, so this would be armature, this would be field, and the field, because they're on the stator here, you can just wire them up directly to some DC power supply to get your field in there. You whirl your coils of wire around, you get your voltage induced, you run it through a rectifier to turn from AC to DC, you run that DC stuff into this electromagnet, and then you can get your main generator's power just by hooking up wires to the armature that's on the stator. Very clever. Brushless alternators take up more space, right? They need this sort of, I've drawn it about the same size, but it tends to be much, much, much smaller because all it needs to do is power this electromagnet. And they use them, you can buy brushless alternators, I know, for larger vehicles. I don't know if anybody sells one sort of that's car-sized. I haven't seen them, but then I'm not a car mechanic, so anyway. E, smoke and mirrors, well, that would be not very practical, though might work, I suppose, depending on how magic you are. Okay, so D is the thing. If you went for A, I mean, I might give you a half point just because it would work. It's just not terribly practical, particularly for replacing a car's alternator, for instance. Okay, last one. We're running a little long here, and we've got current coming up through here, and we're going through these wires, so we're coming up the front and coming down the back of the coil. And we want to know first which end is the North Pole, and then draw some field lines around it to show what the magnetic field looks like. Okay, so if you use your right hand rule, thumb in the direction of the current, and then fingers on the interior of the solenoid, on the interior of the electromagnet curl, so that they're pointed that way. All right. And so that means that field lines are going to be coming out of this end. And they're going to be going into this end. So out here, out, yeah, there we go. And then in here, like that. And so this is the field. And remember that north poles are where the field lines exit, and south poles are where they enter. So this would be the south, and this would be the north of our electromagnet, with the current going this direction around and through all the wires and then back down to the battery. All right, so thanks for sticking with me for the exam review. I hope you found it useful, and I will see you for new material on AC motors soon.